Hi, I am Sarthak and this is a demo for Lab 7 for the subject EE533 under Professor Young Cho. The purpose of this lab was to actually create an ARM-compatible processor core in NetFPGA and to have bubble sort run on it, sort the array and actually put data back into the data memory. The first thing we did was actually create the assembly code for the bubble sort, create the bubble sort, create an assembly for the bubble sort, and then followed by creating a binaries for it. The process of that it will be explained by my friend Justin, while I will explain how the processor was actually designed and how it actually works, along with a little bit of simulation. On the screen, you'll see the diagram that we referenced for creating the ARM compatible processor. Here we utilize the Leg V8 version of the ARM processor, not the ARM V7 or the ARM V8, following the book by Patterson and Hennessy. As you see, we have a PC, an instruction memory, a PC, an adder that actually calculates PC plus 4, the pipe, the instruction memory that sends data across the pipe towards the ALU, and the branch, the control unit, the data memory, and the memory write back stage pipe along with the write back to the register files. Now I'm not showing the HDU and the forwarding units here, but they have been incorporated into the code, as we'll see very shortly. Now going to the code, we'll see that here we have created a PC that actually calculates that actually just outputs whatever the input data it gets. And it also has a check for if one of the bits in the PC is an X, it generates a 0 since we do not want our PC to get corrupted, and then make our pipe jump to some unknown addresses. This here is the PC mux, and this here is the PC offset that actually adds +4 to the PC. What I'll do is actually create it becomes a little easier for us to see the code. Okay. I have shown you the three components, the PC, the PC offset adder, and the PC mux. Then we have the instruction memory. So for the purposes of the simulation, we had this instruction memory initialized with all the instructions that are in a sort. So for example, we'll add 5 to this register. We'll add certain values to these registers, then take a branch, start the inner loop that actually swaps the numbers, and finally at the end we'll halt the infinite loop after the swaps are done. So all these instructions are taken from the Leg V8, which I'll show on the left hand side of the screen. So you'll see that the opcode for the Leg V8 has the LDUR, which is the load register, the store register, which is STUR, the branch, conditional branch on 0, the R-type instructions, add, or, sub, and, or, along with the control table that we utilized. So for the ALU, we have 0, 0, and the operation needs to be an R-type instruction, and the rest of the instructions as follows. Again, as we said before, we utilize this particular formatting for the opcodes, where the opcodes are anywhere from 6 to 11 bits. The registers, the main register RM and R, and the source registers are from 5 to 10 bits, and the bits 9 to 5 will be RN at all times. We do not use a shift amount for now, so we have zeros here and then the destination register that we need to select. For D-type formats for the I-type formats, which is the add immediate instructions, we have a 19-bit immediate field, these two, the source register and the destination register. Finally, this is an example of how the loop will work. This is an example of how the instructions will be saved in the instruction memory, and since we are making a byte addressable memory, the PC is actually, if you see, the instruction memory actually increments for each and every single byte. So for this particular byte, our PC will be +3. For the MSB, we'll have PC. The next byte will have PC +1. The next PC +2, and then finally for the last byte, we'll have PC +3. So essentially, these two out of these two 8 byte out of these 8 bytes, we'll have these 2 bytes as the first 8 bytes of the opcode, and then followed by 2 bits of the opcode in the second byte we have. Concatenating everything, we'll send the data out from the instruction memory into the pipe, and then followed by the ALU and the control operations. Next, we have the control unit. This control unit is the crux of this entire pipeline that generates all the signals for writing to the reg file, indicating what kind of operation to do for the ALU, the control signals for the memory, the data memory, whether to write, whether to read, along with a few other signals that I'll explain, such as ALU op. So if you see on the screen on the right, you'll see reg2 lock, which basically decides what source register to take up. So one of the source registers will be RM. The other has to be selected based on what kind of operation we need. So the reg2 lock will help figure out what kind of register we want. The ALU source will tell us whether the what kind of operand we need. If it's an immediate instruction, we'll need the direct number immediately. So for example, add +8. The 8 number will be selected for this mux. Otherwise, if we need 2 operands, the next second source operand will be selected. Mem2reg selects whether to write into the memory, or if this is a memory operation or a register operation, and based on that, we'd select whether to write into the reg file or not. Finally, we have reg-write, memread, and memwrite. All these 3 signals. So memread and memwrite will tell us whether the data memory needs to be accessed or not. If the memwrite is 1, we'll write into the memory, for example, for store words, essentially. And for memread, we'll have the data from the memory out into the pipe and then towards the register file for our operations to follow. Branch signal indicates whether we need to take a branch and what kind of address we need to have. So for example, this branch signal will actually go in the form of PC source and tell my PC whether to take PC +4 or PC plus offset. And then finally the ALU operation, which will tell my ALU what kind of operation we have, whether it's a D-type, I-type instruction format or not. We broke down the control instruction into this particular format. For example, the branch takes 6 bits of opcode and compares it with the control instruction. The CBZ is 8 bits of opcode. The add immediate is 10 bits of opcode. And then the rest D-type instructions have 11 bits of opcode. Finally, these are the pipes that we created, the ALU that we created for the last lab, and the ALU control. So for the purposes of this lab, we have a few new operations, so we have given arbitrary opcodes for it to parse through. The rest are as the book suggests. These are the memory register, the execution to memory stage pipe, and then this is the memory to write back stage pipe, followed by the reg file. This reg file is nothing but it writes on the neg edge of the clock, and it writes on the neg edge of the clock and reads almost instantaneously, since we do not want a registered output. Finally, we want I'll show you how the simulation works for this. In the interest of time, we'll see that once we run the simulation, these are the signals that I showed you just now. And after the simulation, I'll show you the memory list. If you see on the memory data here, we'll see that the array has been sorted in this particular order where we see C, B, A, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Now this is sorted in the reverse order because the instruction that we gave was in the reverse order. So data memory. So essentially what data we gave was in the exact opposite of this. We gave 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And then we see it sorts in this particular order for us. I'm not going to go through the individual signals because it'll make the video too large, but I'll push all my code to GitHub, and that should help explain what I did. Now, the rest of the lab of the generation of the opcodes, the generation of the binaries, the generation of the assembly level code will be explained by my friend Justin.